Hello again, welcome back. We're going to have a discussion today about chemical bonds. And before we get started, let's take a look at what you should get out of today's discussion. You need to be able to explain the role of electrons in chemical bonding and how they relate to a rule known as the octet rule. The word octet has to do with 8. More about that a little bit later on. Next, you need to be able to differentiate between 3 main kinds of bonds that we'll talk about: ionic, covalent, and hydrogen bonds. And then toward the end, we'll take a look at a particular kind of covalent bond known as either polar or non-polar, and that depends a little bit on how the electrons are arranged in the molecules. So those are what we ought to get out of the day today. First of all, what are chemical bonds? Chemical bonds are energy relationship between electrons of atoms that are reacting with each other. And while that may be a little bit confusing now, it'll get better as we go on. Electrons can occupy up to 7 layers around a nucleus. Those layers or rings are called electron shells or energy levels. And you've probably seen pictures something like this. These rings of electrons, and the electrons, the gray dots in this picture, are the shells or energy levels of our electrons. So more about those as we go through this particular discussion. Electrons in the outer layer are a little bit special. They're referred to as valence electrons, and they are the outer layer of electrons. And the thing that's important about these is they are the electrons that get to participate in chemical reactions. They're the most reactive of all the electrons, and they've got a lot of energy that they can bring. The octet rule basically says that except for the very first shell, which is kind of special, it's full with only 2, the other layers can hold up to 8 electrons in these layers, and that outer layer likes to be full. So as we look at oxygen here, take a look at it. Look at that outer ring. Does it have 8 electrons in it? I made it easy for you. I numbered them, and you can start at the top like 12 o'clock on a clock. 1, 2, 3, 4, 5, 6. There are only 6, and I would ask you, is that full? Well, no. Now, if it can hold up to 8, it could hold 2 more. Now, the number of electrons in this valence shell gives a hint, quite a big hint actually, as to how many bonds an electron can make, an atom can make, sorry. If they try to have up to 8 in the electron shell, and this one only has 6, then it could hold at least 2 more. More about that in a little bit. So again, we're discussing chemical bonds, but the real question starts simpler. Do atoms make bonds or do they not? Some do, some don't. Those that do not make bonds we call chemically inert. They're already stable, they're not reactive, they're frankly sort of happy the way they are. The reason for that is their valence shells are already full. They already contain a full number of electrons, mostly 8, unless it's the inside shell, which would be 2. And since they are utterly non-reactive, they're described sometimes as the noble gases. They do not condescend, they do not deign, they do not care to react with anybody. They're perfectly happy on their own. 2 examples of inert elements are on the screen now. That would be helium and neon. They are both noble gases. Helium is kind of a special case. It's the smallest of the noble gases, and it's full with 2 electrons in its outer shell. Those 2 electrons completely fill that inside shell, and it's the only one that the helium's got. Neon, on the other hand, does have a second layer, but if you notice, that outer layer has 2, 4, 6, 8 electrons, and as such, it's perfectly happy. So both of these are chemically inert elements. They do not react with other substances. And you can see in this picture that I'm pointing at the full valence shell electrons, 2 in helium, 8 in neon. Now, some atoms are reactive because their valence shells are not full. They have less than 8 electrons. If they have less than 8 electrons, they tend to gain, lose, or share electrons in order to become stable. Stable would be being full, and for the most part that would mean having 8 electrons, unless it's the inside shell, which is their outer and only shell, and you'll see one of those in just a moment. In this picture, everything in this list has unfilled outer shells. Take a look. We have hydrogen, top left corner. It's only got one, and that single shell that it has could hold as many as two, which means if it's got one and it needs two, it needs one more. Carbon, on the other hand, has 4 electrons in its valence shell. So let's talk a little about this octet rule. The octet rule basically says that if an atom has 4 or more electrons in its outer shell, it tends to gain electrons to become full. On the other hand, if it's got less than 4, then it tends to donate those to another atom. That's going to leave the shell below that as the outer one, and it's already full because they fill from the inside out. So following those rules, let's take a look again at the atoms we've just seen. Look at oxygen below there. How many electrons in that outside shell? There are 6. Is 6 4 or more? Yes, it is. So oxygen would tend to accept electrons in order to fill the shell. Carbon. Carbon's a special case. It's got exactly 4, and it will definitely accept 4 more to fill itself up. 4 plus 4 would give you 8. Sodium. Sodium has 1 electron in the outside shell, and it can most easily have an outside shell by giving that 1 away, which would mean the inner ring, just below that, would have 8 and would be full. Now that we've got a few rules to go by, let's look at our first bond type. The first bond type we're going to talk about is ionic bonds. Ionic bonds happen when an atom either completely gains or loses an electron and becomes charged. What you need to keep in mind is that an atom, if we're going to call it an atom, by definition has an equal number of protons and electrons. If we gain or lose electrons, then those numbers are no longer equal, and we will have formed charged particles called ions. This is a complete transfer of valence shell electrons from one atom to another atom, and that does indeed create a new thing that's no longer an atom, and we call that an ion. Remember, electrons are negative, and if an atom gets an extra electron, it then has an extra negative charge, and we would call that thing then an anion. Anions are negative because they have extra electrons, so there's more electrons than protons, so they're no longer neutral. If, on the other hand, an atom has lost an electron, then the number of protons will outweigh the number of electrons, and it will be positive. We would call that particle then a cation. Interestingly enough, when we do this, and some particles become positive and some particles become negative, then you have to remember that old rule, opposites attract, and they are going to be attracted to each other. These positive and negative particles will snap together very much like magnets. And here's a great example of that. We have in the left-hand side of this picture, sodium. Sodium, you may remember we saw this earlier, has one single electron in its outside shell, and that's not a stable atom. So it needs to lose that one lone electron. Chlorine, on the other hand, has 7 electrons in its outside shell. It would like to have 8. It needs only 1 more. These two are frankly kind of a match made in heaven. Sodium needs to get rid of 1. Chlorine needs to get 1. So if chlorine gets the 1 extra electron from sodium, then they both become stable. That stability makes them, in effect, sort of happy, but it also changes their charge, because as sodium has lost an extra electron, it's become positive. As chlorine gained an extra electron, it became negative. Now these two things, one positive, one negative, are attracted to each other, and that's actually how we form ionic bonds. They tend to make very regular patterns that we call crystals, where we have positive attracted to negative attracted to positive. And in this particular picture, you see green chloride ions attracted to positive sodium ions. And yes, opposites attract. And this is how ionic bonds are formed. Ionic bonds create ionic compounds. Most commonly, those are crystals, and we call them salts. And probably the most common one that you know about is sodium chloride, probably better known to you as table salt. So ionic bonds are our first type of bond we're going to discuss. Let's move on from there to our next type, covalent bonds. These are a little different. In fact, probably it's better for you to think of the word covalent as meaning sharing. Covalent bonds are formed when two or more valence electrons are shared between atoms. This lets each atom fill its valence shell at least part of the time. And one thing that I've often found useful in thinking of this is think of married families where children from one parent aren't necessarily the biological children from another parent. Let's say mom and dad get married. Dad already has a child, mom already has a child. Let's say dad's got a daughter, mom's got a son, and they all move in together. At this point, even though dad brought the daughter and mom brought the son, you have to stop and realize that, of course, that family has two children. Each of those parents has two children to deal with on a day-to-day basis. So just because they each brought one certainly doesn't mean that they're not sharing both of them. So when you see these, think of the electrons as kind of like kids in a blended family. Let's take a look at the first example. We have here on the left 4 hydrogen atoms. Each of those has one individual electron. Remember, that first shell around the nucleus can hold up to 2. So they're not full, they're not happy, they're not stable. Carbon, over here on the other hand, has 4 electrons in its valence shell. And remember, it can hold as many as 8. Now, let's put these ideas together. The hydrogens each need one more electron. Well, the carbon has 4 it can share. It can share one of those with each of our hydrogens. On the other hand, the carbon needs 4 more. Well, each of those 4 hydrogens has 1 it can share. And again, remember, covalent means sharing. So let's put that concept to use. And what we see here is a methane molecule. Methane has a carbon in the middle and 4 hydrogens. And if you notice here, what we have are single bonds. A single covalent bond is a sharing of 1 pair of electrons. That's a careful thing to take note of here. In covalent bonding, electrons are always shared in pairs. So would there ever be a time where we might share more than a single pair of electrons? You bet. Take a look at oxygen. Each oxygen atom has 6 valence electrons, meaning it needs 2 more so it can have 8. Well, you probably have heard the formula for oxygen. It's O2, which means that a molecule of oxygen is 2 oxygen atoms joined together. Let's see what that would look like. 2 oxygen atoms meet each other. Each needs 2 more electrons, so each shares 2 with its neighbor, which means we are sharing 2 pairs of electrons, and surprise, that creates what we would call a double bond. Let's go one step farther. Here's nitrogen. You may or may not know the chemical formula for nitrogen gas, but it's N2. If you count the electrons, there are 1, 2, 3, 4, 5 electrons in each nitrogen atom's outer shell. 5 is not 8. How many more do you need to get to 8? You need 3 more. So each nitrogen atom in a nitrogen molecule will share 3 with its neighbor, and sharing 3 pairs makes a triple bond. Now, just because these electrons are being shared does not always mean they're being shared equally. Think back to my comment earlier of children in a family. Are there ever, by any chance, favorites between parents and children? Of course there are. Electrons and their nucleus still sometimes have that same kind of idea going on. Let's look at whether electrons are shared equally or not equally. Sometimes they're equal, sometimes not. If electrons are shared equally, then it produces a nice even electrical balance and makes a non-polar molecule, such as carbon dioxide. So we call these non-polar covalent bonds. Carbon dioxide makes a great example of that. We've got an oxygen on the left, that little red ball, an oxygen on the right, the other little red ball, and the gray in the middle, carbon. This is a nice even molecule. It tends to be linear in a nice straight line. They're symmetrical, they're nonpolar, and the electrons are very evenly spread throughout the molecule. In a polar molecule, we actually have uneven sharing of electrons, and that makes what we would call a polar molecule, sometimes called a dipole. Water is a great example, and this happens because atoms in this kind of bond have very different electron attractive abilities. We have two kinds of atoms in this sort of bond. One is often a small atom with typically 6 or 7 valence shell electrons. They're described as being electronegative, meaning that they've got a very strong attraction toward the electrons, and oxygen is a great example of an electronegative atom. Most atoms with only 1 or 2 valence shell electrons, like our hydrogen, for instance, are called electropositive. Sodium's also an electropositive atom. Water, as a result, ends up bent, and we see that red ball of oxygen and the two little blue balls representing hydrogen. And you notice on either end of this molecule, we've got these odd little markers. Looks like a lowercase d with a bent tail on it. And up at the top, that little lowercase d with a bent tail has got a minus next to it. That is actually the Greek letter delta, and it means partial. So the oxygen end of this molecule is partially negative, while the hydrogen end of this molecule is partially positive. As a result, water molecule being partially negative on one end and partially positive on the other end is a lot like, behaviorally, a lot like a magnet. And as a result, water does some very interesting things. Bringing me to our next topic, hydrogen bonding. And this is largely due to this odd behavior we're seeing with water molecules and similar things. Hydrogen bonds are temporary actions between the negative end of one molecule and a positive hydrogen on another molecule. They're sometimes said to not really be true bonds. They're very definitely often temporary.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Interesting stuff, isn't it? Here we see 5 water molecules, one in the center, attracted to 4 around it. And again, they hold together very much like magnets. This is an electromagnetic force, and the positive end of hydrogen is attracted to the negative oxygen. This makes for a really interesting behavior. Water has a surface tension on it, and you can see this insect on the surface of the water. And that happens because water molecules are attracted to each other very much like magnets. That's why if you look close enough, you can see that water can actually be bent. So on our way out, as we kind of finish this topic, let's make sure what you got. Check your understanding. What kind of bonds form between water molecules? Well, since we just talked about it just a moment ago, you probably remember that that would be hydrogen bonds. Next, oxygen and argon are both gases. Oxygen very readily combines with other elements, but argon does not. The reason for that, oxygen is reactive. Its outer or valence shell is not full, so it's happy to react with other elements. Argon does not, and the reason argon does not is because it is one of the noble gases. Its valence shell is already full, so it's stable, so it's not reactive. Now, I'm going to leave this one for you to figure out on your own. Assume we've got this imaginary compound X and Y. That would be 2 different kinds of atoms in case you didn't